Hello everyone. Today we're going to start our series of videos on quadratic functions by looking at the standard form for quadratic functions. I thought that we might go back and take a look at linear relations and see what our motivation is for creating this form of the quadratics. So let's take a look at the two forms that we learned last year for linear functions. This one here we called slope-intercept form, so let's call it kind of short form for that. And then this side we learned a standard form. And there's all sorts of rules associated with this that aren't really that important right now. But we spent a lot of time going from standard form to slope-intercept form. The reason we did that was that in slope-intercept form, you could just pick the slope off the graph and the y-intercept off the graph. And what that allowed you to do is make a graphical representation of that function. So I wanted to look at things a little bit different today. We're going to talk about functions as being input and output machines. You put numbers in and they feed out different numbers. And so it's kind of difficult to look at something that's in standard form for a linear relation and find out what the input-output statement is for it. So if you take a look at this example, you can see that we run into this issue. If I let x be, let's say, 3, then I'm left with 2 times 3 minus y plus 1 equals 0, which would be 6 minus y plus 1 equals 0, which is going to be 7 minus y equals 0. And then you can see that y would have to be 7 to make this hold true. And so 3, 7 belongs to this relationship. It's a set of numbers that satisfies this relationship here. That's fine, but a quicker way of doing this would just be able to have an expression where you could just feed in the x equals 3 and have it spit out a number. And so I'm going to accomplish that by changing this into slope-intercept form. So the first thing I want to do is I just want to subtract 2x from both sides. And I'm going to be left with minus y plus 1 equals minus 2. Then I'm going to subtract 1 from both sides. I'm left with minus y equals minus 2x minus 1. And I'm going to divide everything by minus 1, and that'll leave me y is equal to 2x plus 1. And so now it's much easier to see that this belongs to this. That when I feed in a 3, I get 2 times 3 plus 1, which is equal to 7. So it's just easier to use this to understand the relationship that the function's actually referring to. Functions are just machines. They accept numbers in for x, and they spit numbers out for y. So if we go over here, and we take a look at this machine, and we see that we have a 2, and it spits out a 5. Now there's lots of different relationships that would do this. There's a number of ways we can represent this. This is some unknown machine. So this is some function. Call them functions. And we don't know what it does, but we could label it with something once we know. So this is just going to be our label. And the label will tell us the rule that takes inputs and changes them to outputs. So I can take my 2 and 5 and I can just write them in an input-output table like this. And then if I wanted to summarize this, there's a bunch of different ways I could do that. One way is with a graph. But remember, a graph is just a summary of all the inputs and their resulting outputs. So if I put in a 2, say 1, 2, I could show you that it gave me a 5. 1, 2, 3, 4, 5. So right there, that point there, 2, 5, is such a set of input-outputs. So an example of something that this could do is it could take the inputs, multiply them by 2, and add 1. In that case, I could get more input-outputs if this is the rule that makes this work. First of all, let's just double check that our existing output and input match with this particular label or machine. So 2 times 2 is 4, plus 1 is 5. So this one works. But I could put in a whole bunch. I could put in 0. 0 times 2 is 0, plus 1 is 1. And I could put in, I don't know, let's put in minus 1. So minus 2 times or sorry, 2 times minus 1 is minus 2, plus 1 is minus 1. So we can put all these in now. So 0, 1 would be right there, and minus 1 would be that there. And so if I grab a line, I could just indicate that I could have used any input-output that falls on this line. I could use any of the inputs, and it would give me the corresponding outputs. So, okay, so this would continue forever. So now I could pick them off. So if I don't want to go through all the work of plugging in more inputs and outputs, I can now use this graph in order to get more possible input-outputs. So at minus 2, for example, or let's go minus 3. So at minus 3, 1, 2, 3, 4, 5. Minus 5 would also belong to that relationship. You can double check. Take the negative 3 and plug it into our machine. 2 times negative 3 is minus 6, plus 1 is minus 5. So just thinking about what we did here is we have a machine that has a rule. This rule gives us a set of input-outputs. When we summarize that, that gives us a straight line on a graph, and that's why we call this a linear relationship. And all it really is a rule where you multiply a number by another number and add something or subtract something. So let's take a look at this machine here. This is a different machine. It takes the number here and multiplies it by itself. So whatever this number is, let's say x, it multiplies by itself, x, okay, which is x squared. And so this is the x, and this is the output, which is the y. So if we were to summarize this, let's start off with a table. And this time we'll just slip things, or we'll just switch things up. We'll just call the input an x and the output a y. And we'll just go through some possible values. Okay, so start at minus 2, minus 1, 0, 1. These aren't too hard to do, so we'll just do a bunch. So minus 2 times itself is 4. Minus 1 times itself is 1. 0 times itself is 0. 1 times itself is 1. 2 times itself is 4. 3 times itself is 9. I'm just going to notice something here, is that every time I go here, I'm going to have a slight change between the numbers. So the outputs change by minus 3, then minus 1, then plus 1, then plus 3, then plus 5. Okay? And then you'll notice that the differences between the outputs also change. This one goes up by 2, up by 2, up by 2, up by 2. And so you get this match here. Any machine that has an x squared in it as its largest power, okay, any machine like that will have a second difference that is equal. So this is the first difference, and this is the second difference. So if the second differences are all the same, then you know that this came from an x squared machine. And it could be a more complicated machine, but an x squared machine. And what do we call x squared machines? These are quadratic functions. Also, notice that these go down to a certain number, right? And then they go back up. So it's going to go, I'm not going to do this accurately, but it goes down and up. Okay? So you're going to get a representation of this where you can pick off other values in a shape that we call a parabola. Notice that it's nonlinear. It doesn't look like a straight line. It's a nonlinear shape. Okay, so the very simplest way of doing this would be, okay, so we have this number times itself, right? That's the input-output machine. Okay, so we have the input times itself, and that gives you the output. And this is the simplest one of these. It's just x squared, right? So you get minus 3, minus 2, minus 1, 0, 1, 2, 3. 9, 4, 1, 0, 1, 4, and 9 are the outputs. Okay, and now how do these change? Let's start at this here, because this seems to be an important point, because up above this, all the values for the outputs are the same as the ones down below. So let's just start it here and see what happens as we increase. So the first difference is 1, then 3, then 5. This set we call the step pattern. Okay, and for the base function, or the simplest x squared machine that exists, okay, is y equals x squared, and the step pattern for this is equal to 1, 3, 5. Okay, we'll keep that in mind. That'll come in especially important in our next lesson. So representing our new machine, again, y equals x squared is one way of writing it. And all it is the machine that takes a number and multiplies it by itself. And we're just going to sketch that now. Okay, so I'm just going to sketch that. You should be able to draw a really nice graph of this. I'm just going to do this quick so we can get to a couple other things here. And I'm just going to label this the normal way. This is 0 and 1, 2, 3, and so on. So we have 1, 1, we have 2, 4, and then we had minus 1, 1, and minus 2, 4, and we also had 3, 5, or 3, 9. So we've got 5, 6, 7, 8, 9 right there, and then that gets mirrored over here. Okay, and then we draw that. Nice smooth curve. Mine wasn't so great. Label it with the equation, and you're good. Now, a more complicated machine might look like this, but really it's not really all that different. All you want to do now is you want to realize that this machine is the one that takes a number, multiplies by itself, then multiplies that by minus 2, then adds that to the number times 4 plus 1. So as long as you follow BEDMAS, you're okay here. Okay? Okay, so this one here, let's just make our input-output chart, or our table of values. We've got x and y. Y equals minus 2, x squared plus 4x plus 1. And what I'm going to do is I'm just going to plug in a whole bunch of inputs here. So let's make it minus 3, minus 2, minus 1, 0, 1, 2. Let's see, let's investigate these ones. Okay, so this is going to be minus 2 times minus 3 squared plus 4 times minus 3 plus 1 is equal to minus 2 times 9 minus 12 plus 1. This will be minus 18. Minus 12 will be minus 30 plus 1 is minus 29. Okay, keep going. Minus 2 times minus 2 squared plus 4 times minus 2 plus 1 equals, and you can continue doing this, okay? And so what you'll find is you'll find a graph that looks like this one, and I encourage you to use Desmos to do these types of things. Let me get rid of this graph here. We're going to get, so y equals minus 2x squared plus 4x, and I've already forgotten what it is, so I'm going to go back to it, plus 4x plus 1 plus 1. Okay, so now for this one here, it's difficult to know why this is at 1, 3. It was easy to see before that what we got, that's the one I want. Okay, so it's difficult to see why this would be 1, 3 from these numbers here. There's no direct observation we can make. However, if we look at this minus 2, one thing we notice is that it's negative. This graph opens down. So this graph opens down. Another quick observation we might be able to make is this point right here. If we plug a 0 into this input-output machine, so we have y equals minus 2 times 0 squared plus 4 times 0 plus 1, you'll notice that we're going to get 1. And there you go, there's 1 right there. So we plugged in a 0 and we got out a 1. We call this the y-intercept. Another thing we might be able to observe is, let's look at this step pattern. Okay, so as we go right, let's go right 1. So as we go over one whole, see how here the scale is 1, 2. Let's see how far we have to go down. We have to go down 2. Okay, so we go down 2. Whereas before we went down 1. And we saw this in our investigation as well, is that the new step pattern will be twice that of the old step pattern. So 2, 6, 10 this time. Okay, let's go back to our note. Okay, so when we go over here, the shape when we graph, anything that looks like this, y equals a x squared plus bx plus c, is always going to be a parabola, which is that shape that goes up and then down. Okay. We notice that this can give us information about the step pattern, allowing us to draw subsequent points from the vertex. Okay. This shows us the y-intercept. Now, it's just important that you notice that one thing we don't have is the starting point, right? We didn't know what the vertex is, and we don't really have a way yet of dealing with that. We can't pull the vertex out of here. Just like when we were dealing with the linear relations, this did not give us the slope or the y-intercept. This does not give us the vertex. So you'll have to do some math in order to make that happen, some algebra to rearrange things so that you can easily read the vertex.